Hello, welcome to the TechBeck channel. I bet you didn't know that ancient Indians may have understood the cosmos in ways that still surprise scientists today. We moderns have telescopes, space probes, and supercomputers to help us make sense of it all. But what if I told you that thousands of years ago, long before any of this technology existed, there were people who looked at the same sky and saw something astonishingly familiar? Did ancient Indians really understand space and planets? This isn't just a question of history. It's a question about the very nature of human curiosity and our innate drive to comprehend the cosmos. We often credit figures like Copernicus, Galileo, and Kepler with revolutionizing our view of the universe. And rightly so. They were giants. But the story of astronomy is a global epic, with chapters written in every corner of the world. In this video, we're going to journey back in time, to ancient India, to explore some truly surprising facts from its rich astronomical traditions. We'll look at ancient texts and calculations that seem to defy their era, hinting at a level of cosmic awareness that feels, well, ahead of its time. So buckle up. We're about to dive into a world of celestial mathematics, planetary models, and cosmic concepts that challenge our assumptions about the past. We'll separate fact from myth and explore how these ancient thinkers, armed with nothing but their intellect and keen observation, sought to map the heavens. This is the story of a civilization's profound connection to the universe. A connection that continues to inspire awe and debate even today. Let's get started. Let's begin with a concept that's deeply woven into Indian culture, the Navagraha, or the 9 celestial bodies. You might think, 9 planets? That sounds like a lucky guess. But it's much more sophisticated than that. The list includes the 7 classical celestial bodies visible to the naked eye: the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. These are the wanderers, the grahas, that charted a different course against the backdrop of fixed stars. Recognizing these 7 as a distinct group is a foundational step in astronomy, a feat shared by many ancient cultures. But it's the last 2 that reveal a deeper, more analytical understanding of the cosmos. The final 2 members of the Navagraha are not planets at all. They are Rahu and Ketu. In mythology, they are depicted as a demon's head and tail, eternally chasing the sun and moon to cause eclipses. But in astronomical terms, they represent something far more concrete and mathematically derived. Rahu and Ketu are the lunar nodes, the 2 points in space where the moon's orbital path intersects with the Earth's orbital path around the sun, the ecliptic. These points are invisible. You can't look up and see a lunar node. Their existence can only be deduced through careful observation and mathematical reasoning. Think about what this means. To identify these nodes, ancient Indian astronomers had to understand that the moon's orbit is tilted relative to Earth's. They had to track the paths of the sun and moon with incredible precision over long periods. And they had to realize that an eclipse, a solar or lunar eclipse, can only occur when the sun, moon, and Earth align perfectly, which happens precisely when the moon is at or very near one of these nodes, Rahu or Ketu. This isn't just mythology, it's a brilliant, abstract model of celestial mechanics, a way to conceptualize and predict one of the most dramatic events in the sky. Now let's talk about something truly mind-bending, the speed of light. In the Western world, the first successful quantitative measurement is credited to Euler Romer in 1676, with more precise figures coming centuries later. Yet, in a 14th century commentary on the Rig Veda, a scholar named Sayana of Vijayanagara wrote something extraordinary. He stated, "With deep respect, I bow to the sun, who travels 2,202 yojanas in half a nimesha." Now this is where it gets fascinating. The words yojana and nimesha are ancient units of distance and time. And translating them is where the controversy and the magic begins. Depending on the interpretation of these ancient units, the calculation yields a number that is astonishingly close to the modern value for the speed of light, approximately 299,792 kilometers per second. One common conversion suggests a yojana is about 9 miles, and a nimesha is a fraction of a second. When you run the numbers, 2,202 yojanas in half a nimesha, you land squarely in the ballpark of the actual speed of light. This has led many to claim that ancient Indians knew this fundamental constant of the universe centuries before anyone else. Now, as a scientist, I have to be skeptical. Is this a stunning feat of ancient science? Or is it a coincidence of translation, a retrofitting of ancient terms to match modern knowledge? The debate is fierce. Critics argue that the values for Yojana and Nimesha varied widely, and that we might be cherry-picking the specific conversions that give us the right answer. But even if it is a coincidence, the very fact that a scholar was attempting to quantify the speed of the sun's light, to conceive of it as a finite measurable velocity, is itself a profound intellectual leap for the 14th century. It speaks to a mindset that sought to describe the universe not just with poetry, but with numbers. Imagine it's the year 499 CE. The prevailing wisdom across most of the world is that the Earth is static, the unmoving center of the universe around which everything else revolves. To suggest otherwise would be radical, even heretical. Yet in India, an astronomer and mathematician named Aryabhata wrote a treatise, the Aryabhatya, that contained some truly revolutionary ideas. Chief among them was the proposition that the Earth is not stationary. He argued that the apparent daily motion of the stars from east to west is not due to the heavens revolving, but due to our own planet spinning on its axis. He used a beautiful analogy to explain this concept of relative motion. He wrote that just as a person in a boat moving forward sees the stationary trees on the riverbank as moving backward, a person on Earth sees the fixed stars as moving westward. This is a stunningly clear and accurate description of relative motion, a cornerstone of physics. He was proposing a rotating Earth over 1,000 years before Copernicus published his heliocentric model. While Aryabhata's model was still largely geocentric, he had the planets orbiting the Sun, which in turn orbited the Earth in some interpretations. This single idea of axial rotation was a monumental leap. But Aryabhata didn't stop there. His work also contained hints that the planets moved in elliptical paths, not perfect circles, a concept that Johannes Kepler would formally establish in Europe in the 17th century. He correctly explained that the light of the moon and planets is not their own, but is reflected sunlight. In a world steeped in mythological explanations, Aryabhata was applying logic, mathematics, and observation to build a physical model of the solar system. He was, in essence, doing science. His work laid a mathematical foundation that would influence astronomy not just in India, but across the Arab world and eventually into Europe. So, ancient Indian astronomers had sophisticated models. But could they measure the cosmos? Could they put numbers to their ideas? The answer is a resounding yes. Let's look at a foundational text, the Surya Siddhanta, a comprehensive treatise on astronomy whose origins may date back over 1,500 years. This text isn't just a collection of ideas, it's a manual filled with algorithms and calculations for determining planetary positions, predicting eclipses, and remarkably, estimating the sizes and distances of celestial bodies. It was the go-to guide for Indian astronomers for centuries. The Surya Siddhanta provides a value for the diameter of the Earth. When converted to modern units, their figure comes out to be around 7,840 miles. The actual diameter of the Earth at the equator is about 7,926 miles. That's an accuracy of over 99%. Think about that. Without satellites, without global travel as we know it, they used principles of geometry and local observations to calculate the circumference of our entire planet with breathtaking precision. This wasn't a lucky guess, it was the result of meticulous mathematical work. The text goes further. It estimates the distance to the moon and even the distance to the sun. While the distance to the sun was significantly underestimated, a notoriously difficult calculation that even early European astronomers struggled with, their figure for the moon's diameter was impressively close to the real value. They achieved this by using trigonometry and the principles of parallax, observing how the moon's position shifts against the background stars from different locations. They were using the Earth itself as a baseline to triangulate the heavens. It's a testament to a scientific tradition that was not just observational, but deeply quantitative and mathematical. For many ancient cultures, an eclipse was a terrifying event. A dragon swallowing the sun, a sign of divine anger, a harbinger of doom. But in ancient India, astronomers moved beyond superstition to understand and, crucially, predict these celestial events with stunning accuracy. They knew what was really happening. They understood that a solar eclipse is caused by the moon passing between the sun and Earth, casting a shadow upon us, and a lunar eclipse is caused by the Earth passing between the sun and moon, casting its own shadow onto the lunar surface. This physical understanding was the first critical step. Building on this, they developed sophisticated mathematical models to forecast when these alignments would occur. Remember Rahu and Ketu, the lunar nodes we talked about earlier? These were the key. Indian astronomers knew that eclipses could only happen when the new or full moon occurred near one of these nodes. Their texts, like the Surya Siddhanta and Aryabhata's work, are filled with algorithms to calculate the precise positions of the sun, the moon, and these invisible nodes at any given time. They could predict not just the day of an eclipse, but its timing, duration, and even whether it would be total or partial. This predictive power was a demonstration of the strength of their science. It wasn't about magic, it was about mathematics. They calculated the size of the Earth's shadow, the umbra and penumbra, and how it would fall upon the moon. They calculated the angular sizes of the sun and moon to determine the conditions for a total solar eclipse. This ability to turn a terrifying, seemingly random event into a predictable, understandable phenomenon is one of the great triumphs of the scientific method. It represents a shift from fearing the cosmos to understanding its intricate, clockwork-like mechanics. Our journey through time and space isn't complete without looking at how ancient Indians mapped the celestial sphere itself. Most people are familiar with the 12 signs of the zodiac, the band of constellations through which the sun, moon, and planets appear to travel over the course of a year. This concept, likely originating in Babylon and later adopted and refined by the Greeks, was also a cornerstone of Indian astronomy, known as the Rasi Chakra. They used this system to track the annual journey of the sun and the positions of the planets, creating a reliable celestial calendar. But Indian astronomy added another layer of complexity and precision with a system that is uniquely its own, the nakshatras or lunar mansions. Instead of dividing the ecliptic into 12 large sections, they divided it into 27 or sometimes 28 smaller segments. Each nakshatra represents the portion of the sky the moon travels through in about one day. This system provided a much more detailed and fine-grained map of the heavens, allowing for incredibly precise tracking of the moon's rapid movement against the background stars. It was like having a celestial clock with a second hand, not just an hour hand. This dual system of the 12 solar zodiac signs and the 27 lunar mansions demonstrates a profound grasp of the different cycles that govern our sky. They understood the sun's annual path, the ecliptic, and the moon's monthly and even daily path. This wasn't just for astrology, though that was certainly a major application. For astronomy, it was a fundamental framework for observation and calculation. It allowed them to create star catalogs, build calendars, and provide precise coordinates for celestial events. It was a sophisticated grid laid upon the cosmos, born from millennia of patient nightly observation. So, what have we seen on this journey? We've seen a civilization that, armed with mathematics and relentless observation, reached for the stars long before the age of telescopes. Ancient Indian astronomers, without telescopes, developed accurate models and concepts of planetary motion, eclipses, and time, centuries ahead of their time. From a spinning Earth to the mathematical prediction of eclipses, from calculating the planet's size to conceptualizing invisible points in space that govern celestial mechanics, their achievements were nothing short of extraordinary. This wasn't just a collection of lucky guesses, it was a systematic, scientific pursuit of knowledge. Of course, we must be clear, they didn't have the complete picture. They may not have known about galaxies, nebulae, or the true scale of the universe. Their models were not perfect, but that doesn't diminish their accomplishments. On the contrary, it highlights them. Their logic, their sophisticated mathematics, and their dedication to observation laid the groundwork for modern astronomy. They were a vital link in the long, unbroken chain of human curiosity that stretches from the first person who looked up in wonder to the scientists peering into the deepest reaches of space today. The quest to understand our place in the cosmos is a shared human story, and the contributions from ancient India are a powerful and inspiring chapter. It reminds us that genius is not confined to one time or one place. If you found this fascinating, and I hope you did, please show your support by hitting that like button and subscribing for more amazing science stories from across history and the universe. Keep looking up.